I hope someone's posted on Piazza. The TAs are supposed to be here. I'm going to start the class. Now this is, everybody shut your laptops. We have like 30 people in the room. We have 320 people, 30 people registered to class, of which about 130 are supposed to be in person in this room. And there were several people from section B who wanted to be here. So the fact that nobody is here is telling me nobody is watching the lecture because nobody posts questions on Piazza, right? And I often get questions about things that were discussed in class. And it's kind of absurd. You're supposed to be watching the lectures, and if you're in person, you're supposed to be in this room. And my TAs are certainly supposed to be here. So shut your laptops. And henceforth, I'm going to randomly select some classes which are particularly empty, and I'm going to choose those classes to take attendance, and people who are not in those classes will be not assigned attendance all semester long. I choose to be random because you choose to abuse the system, right? And so that's basically what we will do. Now, can we shut your laptops? Let's start the class.
Wait, Professor, by definition, that's not random. So that's just like, worst case.
Yeah, but the worst case is what you're going to face, okay? Right, so here's a quick recap of where we were. I don't believe I'll be able to pull off the polls because the people who are supposed to release the polls are not here. Right? So, which is super annoying. Here's where we were. Neural networks we saw were universal approximators. We have to train them to approximate any function. They're trained to minimize the total error on a training set. And we do this through empirical risk minimization. We use variants of gradient descent to do this. Gradients are computed through backpropagation, right? So this is what we've seen so far. We also saw that vanilla gradient descent might be too slow or unstable, and better convergence can be obtained by second-order methods that normalize variation across dimensions. You would have discovered this if you saw the slides. Adaptive and decaying learning rates we saw are important. And we will see more of that again today. We saw techniques like RProp that decouple the dimensions can improve convergence, although in principle they really shouldn't be doing so. There should be no guarantee about it, right? Or in the general case. And momentum methods, which we didn't spend a lot of time on, but we will today, which emphasize directions of steady improvement and de-emphasize unstable directions, give us improvements. So we're going to talk about these topics today: incremental updates, trend algorithms, generalization, and tricks of, and in the next class we'll look at some tricks of the trade, okay? So let's start with this. Now here is how we define training. Can I find a chalk? We had some function that we were trying to estimate. And at any iteration, your network itself was some other function. We had a bunch of training instances, and at the training instances, we computed the difference between the divergence between the actual output of the network and the desired output of the network, and we minimized the average of this divergence to train the network, right? So given our input-output pairs at a number of locations, we try to estimate the entire function based only on these samples that we've got. And the way we did it, we start with an initial function. Then we adjust its value at all points. So what does gradient descent really do? It's computing the average error over these training points, right? And then when you adjust the parameters are adjusted to minimize the error everywhere, which means that they're adjusted to, your adjustment would naturally try to increase the value of the function out here where it's below the target, and out here. Guys, if you're looking at your phone, please shut it, okay? And it would try to decrease the value of these other functions where it is overshooting, right? This is what you would expect training to do. And so in the first iteration, maybe it pushes up these boundaries, pulls down the overshoot, and you'd keep, and then the next iteration you'd be computing the new error. Again, they find that it's below at some places, above at other places. You adjust those, and you repeat the process till the error stops going down. Now, the problem with this approach is that the error that we compute is the average error over all of the training points, which is why when you make an adjustment, it's actually adjusting the function everywhere. Now, what would the issue be with doing something of this kind? Can you guess?
So I have no idea.
You should, right, Esteban?
Yeah, the averages across the entire thing, so at very specific points, it'll not approximate that.
It's good that isn't really the case. You would actually get, the more you see, the better you're going to be. The issue is computational. If I give you 100,000 training points, how many points would you be computing the error before you made an adjustment? If I gave you a trillion, yeah, you're not going to be making your adjustments very quickly, right? So there's a poll which we don't have because I cannot be logged. Can someone give me a laptop where I can log in?
What? Math?
I need to get on PIAD's. Okay, skip the poll, right? And my TAs are going to hear about this today. But here is the saves me time. Okay.
Oh wait, you not want us to do
Yeah. So we'll post these slides, updated slides with the polls on the course page, right? Now here is the alternative. We can adjust the function one training sample at a time. Now the advantage with this is every time you see an instance, you make a correction immediately. So what you would do is maybe you pick up this sample over here. You find that at that sample the function is underestimating it. The network is underestimating the function. You adjust your parameters to push it up. And then you pick up maybe the next sample, some other sample, you find it's underestimating again, you push up the function over there. Now you're not going to make giant steps when you do something of this kind, because if you took giant steps, you're going to be adjusting the entire function everywhere for that one sample. You're going to be making small pushes, right? So you can think of it this way. Say I have some kind of a, if you want to visualize it, I have a handkerchief, I'm trying to shape it into a function, into some shape. If you're molding putty, if you had, if you were a robot with 2,000 arms, you'd be grabbing it all over and pushing or pulling it up all at once to adjust it. But then what do we really do? We poke it at individual places a little bit at a time and shape it one piece at a time, right? So the incremental update is basically going to be shaping the function one location at a time. And you'd expect that this would eventually get to the correct answer, right? And so that's what we're going to do. We pick up individual locations, and at each location we'd push the function up or push it down till you processed all the training points. You're going to be picking each one of those. Urvil, get on Piazza, and we've missed a poll. Maybe post it, right? Tell me when you're ready. Okay. So, and eventually when you've processed all of the training points, we will have adjusted the entire function, hopefully with greater overall adjustment than if you just looked at all of them and then made one adjustment. Now, so here's how things would look if you were doing things incrementally. If you did the usual process where you looked at all of the data points all at once, then this is what we call a batch update. We look at all of the training points and then we post our correction. Urvil, can you come up front? And can you post the first poll? So guys, we have a poll. Tell me when it's up. Time's up. Yeah. Okay, I'm going to cut off, right? You're done, right? And so in the batch function, again, the actual loss function you're trying to minimize requires batch updates, the average error over all of the training samples. So this minimizes the total loss over the entire training data. And they actually optimize when you're trying to, when you perform batch updates, where you look at all of the training data before you make an update. What you're optimizing is the actual loss function, but this requires processing the entire training data before you make each update. Whereas in the incremental case, the situation is going to be slightly different, right? So if you were making batch updates, what you would do is you'd process all of the data and compute the average divergence over the entire training set before you made your update. Out here, every time you process an instance, as soon as you compute the divergence for that instance, you make an update. Okay? Now, the iterations can make multiple passes over the data. You've got 10,000 training instances. You're going to go through all of them, make an update. When you're done with all 10,000, you can go back and revisit the original instance. So a single pass through the entire training data is what you would have heard of. The terminology you would have encountered as epoch. And so an epoch over a training set with t samples is going to result in t updates of parameters. Meaning over here, when I'm iterating and saying, perform this until loss is converged, within each loop, I'm going over all of the data. But after each sample, I'm going to make an update. So each time I go over the entire data, this is going to be one epoch. This is going to be an update. So you have t updates within each epoch, right? Now, you can't just do this casually. There are things you have to worry about. There's the business of the order in which you present things. So consider this extreme case. You have these 8 training samples, and the function you're trying to fit is some kind of a curve. It's restricted to being a curve. Now, if I were going through these training instances from left to right, when I process the 4 instances to the left, I'm going to find that the error I've made is large, and I'm going to push the function down, right? And then, so your curve would end up looking something like that. Then I move over to the right, and I begin. So the dotted line is the function you're trying to approximate. The red curve is what your model currently has. So when you move over to the right, what is the model going to do? It's going to push those things down to the line, right? And then the left side is going to go back up. Then you go back to the beginning. You're going to push those down. You just keep oscillating back and forth, right? So this is not a very happy solution. So what would you want to do in this case? What would the appropriate thing be to do?
You shuffle the data points.
Ideally, you want to do one left, one right, one left, one right, right? But the problem is something like that. The problem is, in some high-dimensional space, we have no notion of left and right. So your best shot is to randomly select data points, which gives you a decent shot of doing something from the left and something from the right as you go through the data. So we must sort of go through the data points randomly to get more convergent behavior rather than have oscillatory behavior, which means if we go back to our pseudocode, within each epoch, the first thing you must be doing is to shuffle your data, as Bharat just said. You randomly permute the order of the data. Otherwise, you're almost certainly going to end up getting cyclic behavior, right? Now, so here is what we've seen so far today. In any gradient descent optimization problem, presenting training instances incrementally, one at a time, can be more effective than presenting them all at once, because you get to make for the same amount of computation, you end up making more updates, right? Now, for this, of course, for this to work, things have to be provided in some random order, and this is the. Have you got your hand raised?
Yeah.
Yeah.
I have a question. So, can we go for a hybrid method where we update in batches?
You're gonna. You're predicting me. Okay. All right. So now, and I will see yes, and we'll see why, right? So now this method is called stochastic gradient descent. Why is this stochastic gradient descent? Firstly, it's stochastic because the order in which you select your samples is random. It's gradient descent because obviously you're performing gradient descent, right? So this is stochastic gradient descent. Now, a few questions. Why does this work? Or why would you expect this approach to work? But then will it always work? Are there conditions for this approach to work? And, if the answer is yes, and there are some conditions, let's try to understand what the yes first. And for this, I'll start off by considering a very simplistic explanation that you will often find on the web. Why do incremental updates work? So to understand this, let's try to understand what the gradient itself looks like. What is the gradient? Or consider the derivative with respect to a single parameter. The gradient, right? The gradient is a direction in which you want to move your parameters for the overall loss to decrease. Now, if I have an entire collection of training instances, the direction in which I want to move the parameters to reduce the loss is going to be different for each instance because the error is going to be different at each point, right? So if I have a collection of training samples, those blue arrows show you the direction in which each of the samples suggests that I move the parameters. What we are really doing is computing the average of all of these guys. And that is the direction in which we are moving the parameters, right? Now, let's take an extreme case. All of my training samples are exactly the same. They're just very heavily clumped. So I got T training samples, but they're all the same, right? Now, what is the situation I have? Every one of the training samples is suggesting that I go in the same direction. What will the average be? The same thing, right? So here is what will happen. If I made an update after every single sample, if I were to perform a batch update, after processing T samples, I'm just going to get this one little push for my parameter. Whereas if I were making incremental updates after each instance, then I'm going to end up getting T pushes. And so I expect that this latter case is actually going to adjust the function a whole lot more than the former case. Right? This is why, yes?
You mentioned earlier that in stochastic gradient descent, we might want to take smaller steps so that we don't overjump.
You're absolutely correct, right? So these steps might individually be larger, but cumulatively you'd still expect it to be greater than this.
If they're in the same direction.
Yes, right? So this making sense to everybody? Raise your hands if it is. Right? I'm going to make you do this because this keeps you awake. Now, suppose the situation is not this, you're never going to provide 100,000 samples of the same thing. But suppose your data are all really close. The same principle still holds, right? In the sense that if you made an increment update after each instance, you still expect to see a lot more net benefit than if you waited to compute the average and then take one step. And even if they are not all clumped together, as they get more and more distributed, as they get more and more diverse, you expect this kind of an advantage to remain until they actually get totally random, right? So that is the general intuition behind why these incremental updates work. Now there's more to it than that, and we'll see. Any questions? No? Okay. So how well does it work? Yes?
Wouldn't updating this way be noisy? Because if we update, if there's one noise sample, it would move the gradient in the wrong direction. So the training would not converge faster.
Thank you. You're predicting the next topic, right? So how well does it work? Getting to Aishwarya's point, right? Suppose I was just learning a linear regression. I have all of these training samples. You can skip the text on the slide. If I have all of these samples, what would the linear regression line be? It's going to be the red line right through them, correct? But then suppose instead that I was doing an incremental update one at a time. And so I have all of these points. And I have even managed to learn this line. And now I'm going through the samples one at a time. And then eventually, at some point, I'm going to get to this sample. What will happen to the line? That line is going to become that, right? The next time around, now I get this sample. That line is going to become that. Then I get this sample. Then that line is going to become that. It's going to keep bouncing around. You're never really going to get the correct answer. Particularly if you have noisy samples, this thing is going to behave, very erratically. So what would your solution be?
I don't know.
So anybody want to take a guess? Yes.
So track how much it changed every time instead of found like a threshold.
So there's no threshold away, but track how much we change. What we want to do is we want to say as we keep going through the data, we want our steps to be more and more certain. You don't want this to cycle forever, right? This would clearly cycle forever. And the reason it cycles forever is that the step size you take is always the same the way I wrote it. What you want the step size to do is to shrink with the iterations. At each iteration, you want the step size to be a little bit smaller so that in the limit, even though your individual sample is way off, the contribution, the correction it's going to make is going to be so small that it's insignificant, and the whole thing will stop. So the modification over here is that this is the modified pseudocode. Now it turns out there are two key steps. The first is to randomly permute your data, otherwise you're going to get cyclic behavior. And secondly, you want these step sizes to reduce with each step, not with each epoch, but with each update. Every time you update, ideally your step size must go down a little bit, right? So how fast do you think the step size must go down? To understand how fast the step size must go down, we have two criteria. The first is this. To get an idea, let's look at this. Let's say you have some function. This is the parameter space. So this is W1, W2. Now, your loss function has some derivative. We are taking steps against the derivative, correct? So, and the loss function never has infinite slope. We have sort of made sure that it doesn't have that, right? So this derivative is going to be upper bounded. So if I have some step size eta, and let's say the upper bound is some b, what is the largest step I'm going to take? Eta times b, correct? So now let's say that the optimal solution is out here. This is W opt. And let's say through some mischance, your initial estimate was here. Then what is the requirement on the series of etas to be able to get to the optimal step? Optimal. If every step, let's just assume that every step is going to be has a step size. At every point, the slope is upper bounded by 1, right? Or somewhat close to 1, the magnitude, right? Then what is the criterion going to be? If you keep taking step sizes and they keep shrinking with iteration, right? So the first step size is this large. The next step size is this large. The next step size is this large. The next step size is this large. Will you ever get to the optimal point? So what is the requirement? Can you speak up, please?
Yeah, so the sum of the etas over the number of steps, right, has to be greater than equal to like the distance in some sense.
So the sum of the step sizes must be capable of getting you to that answer, right? What is the worst case distance between where you begin from and where you want to be? Infinity. So you want the sum of your step sizes to be infinite, just to make sure that you have the ability to get to the point no matter where you begin from, right? At the same time, you want the step sizes to shrink, right? You want them to be a convergent series. So the other criterion you want is that the sum of the squares of how do you state that the step sizes must shrink in a convergent manner? If you're close, you don't want to keep running away all the time, right? So you're looking at the two conditions. When you're far away, you want the sum of the step sizes to get there. When you're close, you still want the step sizes to shrink fast enough that you actually stop at the right point. And for that, the criterion you will have, if you work out through the math which Robinson Monroe had back in 1951, that is going to be that the sum of the squares of the step sizes is finite. That's the only way that guarantees that the step sizes keep shrinking fast enough to get to the correct answer, right? So here are the two conditions. You want the sum of the step sizes to be infinite, and you want the sum of the squares of the step sizes to be finite. And you want the step sizes to be as close as possible to where both are satisfied. What is the fastest convergent series that satisfies both properties? I have the answer on the slide, right? What is the sum of 1 over k? Infinity, right? The integral of 1 over x is log of x, right? The integral of, so if you have the definite integral of 1 over x between 0 and infinity, that's going to be log of infinity, which is infinity, right? So, and the integral of 1 over x is basically a continuous version of the summation of 1 over k. So which means this guy sums to infinity. But what is the sum of the squares of k over here, eta k over here? What is the sum of 1 over I squared? Is it 2? Pardon me? Pi over 6? Yeah, I think he's right. Okay. So, but it's finite, right? And so you get the idea that this is the, you basically want your sequence of step sizes to be close to about 1 over k to ensure that you're walking fast enough to get there and far enough to get there in the worst case, and yet it's converging fast enough that you're not going to run off. Okay? So this is another property that must be satisfied. Now, assuming that you have actually run an algorithm which satisfies both properties, yes?
You go back to the previous slide.
So may I see your name?
Sorry,
Just tell me your name. Rohan. Oh, yeah, okay, thank you.
so it says that stochastic gradient descent will converge to a local minimum. Is there any comparison, maybe even empirically, between that and like a single epoch update, whether it achieves a better local minimum because of the stochastic nature of it, or is that like problem dependent?
Okay, you're predicting the next slides, next few slides, right? So you guys are good at predicting me. So here's a little experiment where we are comparing, this is not a network, neural network, this is k-means clustering. Here we are comparing stochastic gradient descent with batch updates, okay? This is the amount of time taken. This is the error that you've got. You want the error to be low and the time to be small. Observe that stochastic gradient descent almost converges before the very first batch update has even been performed, right? So stochastic gradient descent converges much faster. Now what are these bars? When you're performing k-means, you can run this with different initializations, right? Each time you run an initialization, you're going to get an error. So that's actually showing you the spread, the range of values that you got after a certain amount of time, okay? Hey there. You're falling asleep. I think you should go wash your face or something. And don't forget your name tag. Yes. So, all right. So you find two things. The batch descent, actually, the stochastic gradient descent converges much, much faster. But two things have happened. It converges to a poorer solution. And if you look at the variance in the error that you get, it's much larger for stochastic gradient descent than it is for batch descent, right? So can we try to explain this? There is a poll, Urwell 4528. Yeah.
Why do you compare the k-means for the batch gradient descent and stochastic gradient descent?
That's what I had plots for. But actually, the difference really showed up, right? We'll see this the same plot again, right? I think we're done. Okay. So SGD is an online version of batch updates. What we mean by online is incremental. You keep updating your parameters as the data come in. It can have oscillatory behavior if you don't randomize the order of inputs clearly. It can converge faster, but it's very likely to arrive at Fourier optima, right? And the convergence can only be guaranteed if the step sizes shrink across iterations. At the same time, you want the step sizes to be able to sum to infinity. Yes, Abhi?
What's the meaning of the word online?
Online, basically, as data comes in,
Oh, okay.
right? So it's incremental. That's all. I should have introduced the terminology, my bad, okay? So now let's try to understand this behavior. To understand this behavior, let's go back and look at what it is we are actually trying to minimize. What we are actually trying to minimize over here is this shaded area, right? And we are trying to minimize the shaded area while giving more importance to data instances that are more frequent and lesser importance to data instances that are less frequent. Okay? Yes?
In the first poll, you talked about like the actual loss and like how the actual loss was like computed in the batch. But in the batch is still like a discrete case.
So that is the loss. The loss is what you get off your data.
Oh.
The expected divergence is the theoretical thing that we're trying to minimize. That's the shaded area, right?
Okay.
So this is not really the loss.
Okay.
The loss is your approximation to this guy, right? Correct. So now let's look at what this is. So at each point you have a divergence. You're taking the integral of the divergence over the entire training data, the entire space. And that is the shaded area that you're trying to minimize. Now if you consider the divergence itself, if I consider the divergence at any particular location, if I just randomly chose a sample, right? That sample could be here, and then the divergence would be large. If I randomly chose a different sample and the sample were here, the divergence is going to be small, right? So depending on where I choose a random sample, the actual divergence value that I'm going to get is going to be very different. So if I plotted the distribution of these divergence values for a single sample, the distribution is probably going to look something like this. It has an average and it has a variance, correct? Now, if your function is perfectly estimated, then what is this average going to be? Ryan?
It's going to be equal to the divergence of 1, all them together.
So I'm saying the function, if the network nailed the function, it got it just right, what is the average divergence going to be? 0, right? There's 0 everywhere. What is the variance of the divergence going to be? Also 0, right? So the closer your function is to what you're trying to estimate, the smaller the mean and the smaller the variance, right? So, but for any given function, it's going to have a mean and it's going to have a variance. Everybody with me so far? Right. Now, was there a hand? No. Okay. When I'm training, now let's hold that thought. This is the divergence, and this is the probability of the divergence for a single sample, right? Now this is the term that you would like to minimize at each point. This is what we are trying to approximate, correct? This is what we're approximating. Now I'm going to switch gears briefly. We'll come right back. Suppose I have a distribution, any odd distribution, and I choose a single sample from it. What is the expected value of the sample? Aparajit, can you tell me? What is the expected value of the sample if I just choose a random sample from a distribution?
The mean of the whole thing.
That is going to be just the mean, right? So this is going to be the expected value of whatever. Let me call this D. What is the variance for?
You subtract the mean from the individual training sample.
No, but what is this? What would the variance of the sample value be if I just randomly chose a sample? It's just going to be the variance of the distribution itself, right? So this is variance of D, right? Now, suppose I chose 10 samples, right? Or I chose some n samples, right? And I chose these n samples at random. They're independently drawn. So if I'm choosing n samples and I take the average, so I say S1 plus S2 plus S3, and I take the average, what is the expected value of this guy going to be? It's the same, right? If I take the expected value, this is going to be 1 over n times expected value of D plus expected value of D plus n times, which is going to be 1 over n times expected value of D, which is the expected value of D. So which means that if I choose n samples and take the average, that is going to be pretty much this value, meaning this is the expected value. It doesn't mean that that's what you're going to get. It means that if I take n samples and take their average, and if I repeated this experiment millions of times, right, and computed the average of these averages, that's going to still be the same guy. Or alternately stated, if I chose n samples at a time and took the average of n samples, that is going to have a distribution, and the mean of 1 over n summation I sample I is going to be the same as the other guy, right? Now suppose I choose these n samples at random. What is the variance of the average going to be? He's jumping to the answer, but even before that, right? Let's take that in a two-step process. Suppose I take my sample S and multiply it by alpha. What is the variance of alpha times S? Alpha squared S, correct? So the variance of alpha S is alpha squared variance of S. Now suppose I have S1 plus S2 as n. What is the variance of n independently drawn samples? Someone at the back, can you tell me? Sichi, what is the variance of 10 independently drawn, sum of 10 independently drawn samples? It's going to be variance of S1 plus variance of S2 and so on, which is going to be n times the variance of S, right? Now suppose I take this and I multiply this by 1 over n. What would the variance be? It's 1 over n squared of this, correct? So that is going to be 1 over n squared of the variance of these, which is going to be n over n squared variance of n, which is variance of S divided by n. Okay. Now going back to this situation over here, if I drew n samples at a time and took the average of these n samples and I plotted the distribution, what is that distribution going to look like? The distribution is still going to have the same average, right? But if this were the variance V over here, this is going to have a much narrower variance. It's going to be V over n. This clear to everybody? Raise your hands if it's clear. Okay, so now let's go over here. This guy, we saw that this loss is the average of a bunch of training samples, right? So the expected value of the loss is basically the expected value of the divergence itself. So which is why we are going to say that the empirical risk, which is what we call, which is the loss, which is basically your empirical estimate of the shaded region, that's an unbiased estimate of the expected divergence, because on average it's going to have the same value as the expected divergence. There's no guarantee that it's actually going to be the expected divergence, right? It just means that it's in expectation. If you repeated the experiment zillions of times, on average you'd find that as a correct answer, right? So it's an unbiased estimate. though there's no guarantee that minimizing it will minimize the expected divergence. It's just a sample, right? But then the variance of the empirical risk is 1 over n times the variance of the divergence itself. So here is the beauty of it. As n kept increasing, eventually what is this guy going to become? It's just going to become the expected value, right? So if you had infinite n, then your loss is going to be the actual function that you're trying to minimize, right? But if you have a finite number of n, there's a variance, and it's going to be variance. Yeah, yes, Oren?
So this assumes that you're able to sample from the whole function with the I guess the true probability.
Yes, and the assumption is if you're collecting data naturally, that's what you will actually be doing, right? So this so far so good, right? And so you want n to be large because you want the samples, the loss that you get to be representative of the expected divergence which you want to minimize. Now when I'm doing stochastic gradient descent, performing stochastic gradient descent, this focuses at each point, at each update, how many samples am I considering when I'm performing stochastic gradient descent, Yulo? So what is the expected value of the loss? Ben, maybe you can tell me? Okay, you can go ahead. What would it be, Jay? If I have just one sample and I'm computing the loss on one sample, what is the expected value of the loss? That's the same, right? It's basically you're drawing a sample from the distribution, correct? What is the variance of the loss? It's going to be basically the variance of this distribution itself, because it's like drawing one sample from the distribution, correct? And so when you compare these two guys, which of them has the lower variance? The average or the single sample? The average, right? So the sample divergence is an unbiased estimate of the expected error. The variance is the variance of the divergence itself. This is n times the variance of the empirical average minimized by the batch update, which sort of explains this behavior, right? That this guy has much lower variance than this one does, right? Or that's all very great for math, you know? But let's try. I never understood math, although I teach it. I like to see pictures. So let's try to see what this means in a practical sense, okay? The blue curve here is the function we are trying to approximate. The red curve is the approximation by the model at a given, for a given parameter, okay? Setting of the parameter. So the shaded region is the error. Sometimes the shaded region is positive, it's blue, meaning the true function is above the estimated function. Sometimes it's red, which is negative, where it means it's negative, right? We want to minimize the shaded region. If I've got a collection of samples, training samples, I'm going to be minimizing the sum of these short line segments, the lengths of these line segments. That's what I'm trying to do. And if this were the specific set of line segments that I got, then the model parameter update will figure out that it has to push up the parameter function here, it has to push up the function here, it's going to push down the function in between these two, right? And in between, unfortunately, it's also going to push down the function in the yellow region and make it worse, in that central blue region and make it worse, right? The specific behavior of the update is going to depend on where you get the samples, right? So if you got these samples instead, it's going to push the function up everywhere. It's going to miss the fact that it's actually going the wrong way in some locations, right? If you got these functions instead, these samples instead, then it's going to push the function in the wrong direction overall. So although in each case the number of samples you have is the same, the manner in which the update behaves is going to be very different. There's a variance in how the update behaves, right? So how would you solve this problem? What is the best, easiest way to fix this? More samples, right? The more samples I have, the more decent the update behavior is actually going to be, right? When I'm doing this with only one sample, you can see how bad it is. If the sample ends up there, you're going to decide there's nothing to do. If it ends up here, you think I've got to push the function up. If it ends up here, you're going to decide that I've got to push the function down. And so overall, you can see how, when you're just updating based on a single sample, the actual behavior, what you do is going to be very dependent on where the sample ends up, and there's a large variance to what happens when you make the update. And that variance is much smaller when you got a larger number of samples. So all this math is fine, but intuitively you can immediately see what is happening in this case, right? And so now, that sort of explains this behavior, right? When I'm using stochastic gradient descent, I'm sort of bouncing around with what I'm going to do. Whereas when I'm using batch updates, I'm being a little more consistent in my in my updates, which is why the batch update actually has much lower variance. It has the variance is 1 over n of the variance that you get with stochastic gradient descent. So SGD uses the gradient from only one sample and has high variance, but also provides significantly quicker updates. Is there a good intermediate, right? And the good intermediate is, I'm still going to, this is what I think Abhi mentioned, right? That we're not going to, we don't need to be making an update after every sample. We could be working on small numbers of samples at a time. This is what you're all familiar with in your homework. This is what we call the mini batch update, right? So you're not going to be choosing all of the samples. Obviously, you can't wait for all of the data to be processed, but you're going to be using subsets and then making updates after the subsets. As before, you still have to randomly shuffle your data before choosing your subsets, right? And so here, what you would do, for instance, you'd maybe the first update, you pick these points. And when you pick these points, you've got to increase the function here and decrease it there. So you make those adjustments. That's also going to modify the function elsewhere, right? So the next update, you choose maybe a different group of points, maybe these guys. And then you have to increase the function over here and continue to increase the function here. And so you can keep doing this in small groups of samples. And you can expect to get overall better behavior. The pseudocode over here just basically says that now you're going to be processing a batch of samples. And you're still going to be averaging the divergence over the batch, mini batch, and then making your update. You still have the same requirement that you have to be shrinking your step size, because this is fundamentally no different from the stochastic gradient descent framework itself, right? And you still don't have the requirement that you have to shuffle your data, otherwise you can end up with cyclic behavior. Okay, now how large do we want our mini batches to be? Yes, Kunal.
Should we reduce the step size after the entire epoch or even after each mini batch?
So
Because we will give preference to the batches which came
in principle, you're drawing each mini batch randomly, which would be the same as shuffling it once after each epoch, because if you just sequentially group them, it's going to give you the same effect, right? So now if you shuffle them and then take sequential batches, that's sampling without replacement, but it's not a big difference. Okay. So now let's look at the statistical behavior of this and go back to math now that we've actually seen the pictures. Yes, Jeffrey.
But should we, so do we still have the requirement to reduce our step size to guarantee that it converges to optimal?
You still have the same situation, right?
So in this case, our learning rate schedule should be, the decrement in step sizes should happen after every batch.
So you can think of this, if I'm looking at mini batches, right, you can think of it as many samples where each sample is a collection. So conceptually, it's the same as stochastic gradient descent, right? And so as a result, all of the requirements still hold. Okay. So now, when I'm looking at the math, what happened over here? The mini batch loss is the average divergence over the mini batch, right? What is the expected value of this one? Eric, what is the expected value of the mini batch divergence?
The expected value.
Someone else help me? Yes.
Is it the same?
It's going to be the same, right? Instead of n, you replace it with b. Nothing really different, right? So what this means is that when I have when I'm taking the average over B samples, and if I plot the distribution of this average, that is going to have an expected value which is the same as this guy, right? What is its variance going to be? Talab, can you tell me?
The same.
Same as what?
The stochastic gradient descent.
No, but I'm averaging B samples. Yes, Fan?
Maybe 1 over B.
So this is going to actually be not as narrow as this guy, because here I had many more samples, not as broad as this guy. It's going to be V over B, right? So if the variance for one sample was V, the variance for n sample is V over n, the variance for B sample is V over B, right? And so now if I begin, and obviously you want this variance to be as small as possible. So now if I actually plot this, you will find that this is the variance of the batch, and this is batch size. So for a batch, I'm going to start at 1. For a batch size of 1, you start at V, right? For a batch size of n, you're going to be at V over n, which can be quite small depending on how large n is. And as this one goes, it's going to fall off really fast. It's going to fall off as 1 over B, right? And so what this means is that by the time you get to maybe B equals 100, this is already V over 100, which is probably not going to be very large, very far off from V over n, right? And so you can see why when you begin working with mini batches, so long as your mini batches are sufficiently large, the variance that you get from a mini batch is not significantly different from the variance that you get over the entire training data. And so you can expect the behavior to be much less erratic than if you were working on making updates one sample at a time, right? And so this is basically what you will find. The mini batch loss is also an unbiased estimate of the expected loss. The variance of the mini batch loss is 1 over B of the variance of the divergence itself, which will be much smaller than the variance of the sample error, right? And so that gives us a different kind of behavior. So this is what we got with batch updates. This is what we got with stochastic gradient descent, where you were making an update after every individual sample. But then when you begin working with mini batches, it still doesn't get as low as this guy. Often it will. That depends on the specific experiment. But what you observe is that the variance that you get across runs is much smaller than the variance that you get across runs out here. And so, can you shut your laptop? Or are you looking at the slides? Okay, fine, right? So the variance that you're looking at that you get across runs is going to be much smaller than the variance that you get when you're just making an update after every individual instance. At the same time, it seems to be converging much faster than batch descent. And this is the behavior that you will generally find, which is why we work with mini batches, right? So now there's also this issue of how did I actually compute these plots? I didn't, somebody else did. But then how was this loss? These are errors plotted on the entire training data. That's what you want to compute the loss on, right? If you want to compare these things, you want to compute the average divergence over the entire training set and see how it varies for different parameter settings. And these are what the parameters are when you use SGD. This is what you use with full batch. This is with mini batch. But then computing the error in this way is kind of pointless, because although you made an update after just seeing one sample, you still processed all of them just to compute the error, right? So you wouldn't actually do that. You'd have other ways of estimating the error, like divergence or classification on some held out test set, or using a running average and things like that. Anyway, these are just the mechanics of it. But the concept of why mini batches are better than either SGD or full batch is shown by this plot. And it's also obvious that you really want the mini batches to be as large as possible, meaning you want to put as many as you can put into your processor. But then there's also the math of it that beyond a particular size, expanding the mini batch anymore is not really going to buy you very much, because you've gone past the knee of the curve, right? And so in practice, training is usually performed using mini batches. The mini batch size is a hyperparameter that you'll optimize. And the convergence also depends on the learning rate. Again, the learning rate needs to have this behavior, right? It sums to infinity and square sums to something finite. And if you have something like having a fixed learning rate for some iterations, then you bring it down by 10 for some iterations and so on, you will find that this actually satisfies the property that it sums to infinity and is still square summable. Anyway, and advanced methods have more adaptive updates. You will be encountering some of these when you do your homeworks. Okay? There's a poll. Okay, 5 seconds, guys. Then I'll move on, right? And I've counted 5. Okay. Of the statements, only one of them was false. It said mini batch descent is faster than SGD when the batch size is 1. When the batch size is 1, they're both the same thing, right? The rest are all true. Now, so here's the story so far. Presenting training instances one at a time can be more effective than full batch training, provided they're presented in random order. But for this SGD to converge, the learning rate must shrink rapidly with iterations. Otherwise, the learning will continuously chase the latest sample. SGD estimates have higher variance than batch estimates for the reasons that we just saw. And so mini batch updates that operate on batches of instances at a time have lower variance than SGD. In theory, if you actually look through the math, the convergence rate is supposed to be worse than SGD, but then the fact that you can process data in batches ends up giving you a benefit anyhow. So or in terms of compute time, it ends up being more effective because you can actually do batch processing, right? You say that?
When we do mini batch, do we shuffle the remaining instances and then choose new?
You don't need to, because you only have to shuffle the instances once at each epoch, right?
Okay.
You don't have, because you're not revisiting samples. So, yes, Neil?
It said in the poll it said mini batch gradient descent is an online training algorithm.
It is an online training algorithm. You're not waiting for the end of the data. It's online with a little bit of a delay, right? 10 samples at a time or 100 samples at a time. It's still online. Okay, so now we'll move on, and now we are going to revisit something that we saw towards the end of last class, namely momentum, right? Here's what we said about momentum. And so we said that if you just only followed the latest gradient, then in a gradient descent update, you can have some pretty wacky behavior. Where's my chalk? These things walk, okay. So in the sense that we saw exactly how these convergence issues can arise, right? That depending on the step size and considering the fact that the curvature of the loss function is different for different components, you can end up having updates which look like so, right? Whereas your ideal update, starting from here, should have been something that went this way, right? You're walking a lot more, traveling a whole lot more for much less effect. So what the momentum methods do is, so what's happening over here? In the vertical direction, there's a whole lot of traveling for nothing. In the horizontal direction, we're doing just fine, right? So we need some mechanism of sensing which directions we are moving around pointlessly in to reduce the, movement in that direction. We want to sense which directions we are actually getting fruitful gain from and increase the movement in that direction, right? And so one simple way of doing this is if you actually took an average of all of these guys, you're going to find that all of these positive and negative oscillations are going to cancel out over here. Whereas in this case, you're getting the right thing. You would actually end up at the same spot, right? If you took that. So now obviously you're not moving as you compute the derivative. So the way you would do it is to maintain a running average. And so we all know what a running average is. The running average of any variable is, this is if I call x bar the ith running average of the variable, that's simply going to be some alpha times x bar I minus 1 plus 1 minus alpha times xi. This is the standard formula for the running average, right? Or in fact, you can correct it. There are other ways of writing it, but this is the general formula. So here's what we're going to do. What is our variable over here? This is the step size, the update that we are making when we are adjusting our parameter. And that's what these things are. These are all of these movements are your updates. The first one is this, the second is this, and so on. Those are the ones we want to average, right? So we're going to maintain a running average. The update, the kth update, I'm speaking of the step, is going to be a running average of the k minus 1th update and the step suggested by the current gradient, right? So typically, this is going to be 0.9 times the past step size plus the past update plus some step size times the current suggested update. Now I've got a minus over here. Why is this a minus? Changsheng?
Because in that direction, I feel.
Can someone give me a 2-word answer? Yes. It's gradient descent, right? You're going against the gradient. Wake up, right? So that's all it is. That's why. So although I say I'm adding the step is always against the gradient. It's minus gradient, right? So this is what momentum updates do. So here's what we do. Let's say the previous step size at the current iteration was this. Then to compute your next step, what you would do is compute the gradient over here. The gradient, as we saw, is going to be orthogonal to the level set at each point. So the gradient here is going to be orthogonal to this ellipse. It would be in this direction. Actually, the gradient would be outwards, pointing this way. And so the negative of the gradient is going to be the blue line. But you don't just go there. To that, you add a scaled version of this guy. And that's going to be your final step. Right? So, yes?
Related to the lecture, is there a science sheet going around?
No, not today, because clearly we are shorthanded, right? We need 2 people and we only got the Piazza guy. All right. Were there any questions on Piazza? No, okay. So this is how momentum updates work. Make everybody understand what's going on here, right? Now, so you can actually do something better, which turns out to be more optimal. This is the so-called Nesterov method. Now observe what's happening in here. At the current step, mind you, this too is a running average, right? The first red line is also running average. The first thing you did was to compute the gradient step, which was 1. And then the second thing you did was add a scaled version of the previous step to get the final step, right? You can change the order. And to change so this is kind of maybe not the most optimal thing to be doing, because really the fact that you continue to move in this direction means that maybe we should have considered a different gradient. So the reversed approach is something like this. You have a current step. Then the first thing you do is you extend the current step a little bit. So beta times the current step. Then compute the gradient at the extended location. and this is going to be your final step, right? So you just change the order. Earlier, first you computed the gradient update, then added the previous, the scaled version of the running estimate to get your new estimate for the update size. Here, first you add the scaled version of your update, and then you compute the gradient. Okay, it's just a minor change in order of operations, and that gives you the final step. So if you so when you actually write out the update rules, it turns out to be a little more crazy, in that the step size over here is going to be the increment, which is this red line, plus the gradient update computed after taking the increment, which is wk minus 1 plus beta. Yeah, this is the previous step, right? So although the equation looks very complicated, this is basically all that you're doing, and it turns out that this actually ends up being more optimal. It's provably optimal under several conditions. So this was an example I got from one of Hinton's slides. Here on this thing, the blue curve shows you the updates you get with standard momentum. With gradient descent, it's going to be crazy anyhow. But if you use momentum, you come here, then you compute the gradient, then you add the scaled version of the previous step, and that takes you to this point. And so if you keep following this, if you find that you're going to sort of circle around to the optimum. Whereas if you just change the order, you first extend it and then compute the gradient. That's your new step size. Then you extend that and you compute the gradient. In 2 steps, you get to the optimum. So just the simple change of order can make it much faster. Right? All very fine for functions of this kind. But all of these are doing something very, very important. That's a general idea of momentum and Nesterov, right? All of these are doing something very important for us, particularly when you have things like stochastic gradient descent. In stochastic gradient descent, your gradient naturally has noise because you're always following the gradient from the latest sample or the latest mini batch, right? So the random fluctuations of the gradient are going to be much larger than in the case of a batch. So in a stochastic gradient framework, having this kind of smoothing is going to be much more important than in your conventional updates. Can you tap it? Okay. So because momentum smooths out these variations. So this is important. And so basically, in momentum, if you're using the simple momentum method, this gradient term that you're computing in momentum, that's going to be a stochastic gradient. It's not the gradient over the entire batch. It's the gradient over the latest sample or the latest mini batch. Or if you are using Nesterov's method, this term over here is going to be either the gradient, the gradient over the mini batch or the gradient computed at the last sample. Now, momentum and Nesterov's method improve convergence by normalizing the mean of the derivatives. What do you mean? I'm taking the running average of all of the gradients, correct? So all you're considering is the expected, the average of the gradients. And that does help, as we can see. But there's a second term which also informs us. Now, when I'm looking at the average of the gradients, all I'm doing is figuring out what the step must be, right? I'm averaging the step. But then there's a second thing. Let's look at some behavior of this kind, right? If I'm looking at behavior of this kind, it tells me that I'm swinging around a whole lot more in the vertical direction, but I'm moving consistently in the horizontal direction, right? So analyzing the swing should tell me that maybe I should be taking smaller steps in the vertical direction and larger steps in the horizontal direction. So we are not speaking at this point of the update deltas. We are speaking of the step size for the update. And the fact that things are swinging around like so tells me that in the vertical direction, there is too much motion. So maybe my step sizes are too large. I should take smaller steps. In the horizontal direction, I'm going consistently. I could take larger steps, right? So how would we quantify this? What is the best way of quantifying the net movement? The thing that's happening over here is that there is the actual movement versus the net movement. And in the horizontal direction, the actual movement is very close to the net movement. In the vertical direction, the actual movement is a whole lot more than the net movement, right? So if the actual movement is a lot more than the net movement, you want to decrease your step size. If the two are consistent, you want to increase your step size, or at least retain it, right? So this is the principle that we're going to use. We're going to sort of, we have the entire, skip what's on the slides. The intuition is very clear. We have an entire sequence of techniques which look at the second moment of the movement, right? So the problem with here is that if when you compute the average, in the vertical direction, the average cancels out, and it tells you that if you just looked at the average, you don't really realize how much you're swinging by in the vertical direction. All you realize is that you're going up and down, and that you're averaging things out. But then if you considered the second moment, the sum of the squares, that is going to tell you that I've moved a whole lot in this direction. And in fact, if you compare the second moment with the average with the root mean squared value, that should tell you what is the actual benefit you're getting related to how much you're moving. Is that making sense to you? Right? Raise your hands if it is. Okay. It's falling asleep. All right. So now, I really think you should go wash your face. Now, now, this is what we're going to try to do, right? We are going to find a second moment, and if the second moment is high, we are going to scale down the step size in the directions in which the second moment is high, and we're going to sort of retain it or scale it up in the directions in which the second moment is low. So that gives us this technique that we call RMS prop. Again, the updates are by parameter for individual parameter. And what we will do is maintain a second running average. We want the average second moment, right? So we're going to maintain a running average of the second moment. And we're going to compute the mean squared, root mean squared value of the actual movement. So it's the square root of the running average of the second movement. So here's what we would do. At each step, this is your running average of the second moment. You basically average the current, you take a weighted sum of the current estimate for the running average of the second moment and the square of the current derivative. So this is maintaining a running average of the second moment. And the root mean squared value, of course, is you're going to take the square root of that. The plus epsilon is just to make sure that you don't have a division by 0. And so observe that your step size is now being scaled down by the second moment. And this naturally takes care of swings. And so places where the second moment is, where you're moving in directions in which you're moving a lot more than you need to, the step size will shrink. In the other directions, it's going to shrink not so much. Now, this thing is very similar to R prop. Suppose I have a loss function which is a continuous sheet with the same slope, right? What is this second moment going to be? If I just have a plane, what is the second moment going to be? So the second moment is not going to be 0. It's just going to be the square of the slope, right? At every point, it's always the same slope as you keep going down. And so the second moment is going to be just the square of the slope. The root of the second moment is just going to be the slope, correct? And so when you take this ratio, these two will cancel out. The only thing that will remain is the sine of the slope, right? And so basically, you're always going to be walking, and the steps you take will be only considering the sine of the slope. What was the update rule that did that we saw in the last class? R prop. So this is RMS prop is basically just an extension of R prop. That's where even the name came from, right? Now, the thing here is that, yes? It's not the mean squared value. It doesn't say mean squared error, mean squared value of the derivative. Mean squared, right? So root mean squared. This, which one? So this is mean squared value. This is the squared value of the derivative. You're maintaining an average of the squared value. Is the squared value of the derivative. It's still the regular derivative. It's not the second derivative. We are speaking of just the step size, right? The step sizes keep going back and forth. So you're taking the squared value of the derivative. It's not the second derivative, right? Now, the issue here is that this guy is adjusting the step size. It's taking the second moment into consideration, but this is basically just gradient descent, right? This is not momentum. We know momentum helps too. Yeah, you can?
Yeah, I'm confused. Is the two second order derivative or the...
It's a square of the derivative. I think if you the squared derivative, I've actually mentioned it out here, right? It's the square of the derivative, not the second order derivative. I've explicitly stated it on the slide. I should have been careful, right? So now, now we can do one more. We can also, instead of using just the instantaneous derivative over here, we can also factor in the expected value of the derivative itself, just like in the momentum case. Yes, Jeffrey?
What's the purpose of the epsilon in the...
That's to prevent division by 0, right? So now, instead of just over here, this is just gradient descent, except the step size is being modulated by the second moment, right? Instead of just using the raw derivative over here, you could replace the raw derivative by the running average of the derivative itself. This is combining momentum methods by an adaptive step size, with an adaptive step size, right? And so now you would be maintaining a running average of the derivative. You would also be maintaining a running average of the second moment of the derivative, right? And the update is simply going to be, instead of using the raw derivative over here, you're going to be using the average derivative, and the step size is also going to be modulated by the RMS value, root mean squared value of the steps. Now there's an extra term over here, which is the you don't actually use the raw running average. You scale it down by 1 minus delta to the k. Now that's a heuristic. That's a bit of a hack. And the reason for that is that if typically your delta values will be large. And if your delta value is close to 1, then this 1 minus delta is going to become 0, right? Which means that you don't really make an update at all in the early stages of your algorithm. So to prevent that from happening, they have a division over 1 minus delta to the k. So in the first iteration, it just becomes 1 minus delta divided by 1 minus delta. You cancel things out. So in the early iterations, it sort of regresses to conventional gradient descent. But then after a while, you begin using the running averages to make your updates. But the basic idea is this. Now you have an adaptive step size, where the step size is inversely proportional to the RMS value of the derivatives, just to make sure that you sort of have smaller steps in directions where you have more variations, and the derivative itself is just, again, a running average, right? I'm going to go a couple of minutes over. So there are many algorithms based on this general principle. All of them basically have different flavors of exactly the same paradigm over here, and you might have encountered them when during your recitations. You have Adam, Ada delta, Ada grad, Ada max. They all work more or less the same way. They all have more or less the same underlying principles, right? And which one you want to choose is a matter of choice. I'll skip this poll. I'll stop with this couple of simulations that Alec Radford has on his website, where he's comparing the behavior of many different algorithms. So I'm going to spend 2 minutes, go over by 2 minutes, because this is worth spending your time on this. over here he has this function called Beal's function. Beal's function has an optimum value over here. All of these algorithms are starting from the same point. And you can see the manner in which the different techniques arrive at the minimum. And you'll observe that SGD, stochastic gradient descent, which is always following the current gradient, takes its time getting to the optimum. Whereas momentum or Nastrov's method or our RMS prop that we saw, or Adam, they all sort of get there pretty quickly. And the interesting one is Nastrov's method. You'll observe under many conditions, this is the optimum one, right? So because it's not actually looking at variations, it initially runs off in the wrong direction, but then quickly gets to the optimum, right? Momentum goes and wiggles around in some other place, but eventually gets to the optimum as well. In the big picture, maybe all of them get to the optimum at the same time. In fact, Nastrov's is their fastest. Whereas SGD spends its time doing something silly, right? Now, this is a much nicer function. This is Beal's function, right? This is a saddle point. And you can see what's happening. Clearly, so you want to be going down here, and SGD sort of oscillates around and finally finds a place where the derivative is 0 and it's happy. It's going to sleep, right? But then momentum and NAG, which don't actually consider the second moment, follow the same trend as SGD. And so they spend the initial few cycles moving in the wrong direction, but then eventually come to a point where a minor perturbation simply sort of quickly ramps up, and in the end they end up being really fast. So you can see how quickly this fly down, right? Now something like RMS prop. RMS prop, if the function is a continuous slope, the step size never changes, right? Because the slope is continuous and the RMS value is also continuous. So you can see how RMS prop, this black line, is going down very steadily because it's pretty much a constant slope. Whereas if you have the more adaptive techniques, they're going to realize that it's a constant slope and speed up. So there's some very nice intuition to be had. And again, same thing with a saddle point. You can see how SGD ends up searching for some flat point over here and spends its time here, whereas the rest of them sort of find the direction of the steepest descent. And in fact, although we don't have time now because I've run over time, we could have explained the behavior of every single one of these algorithms based on the slope that you see, right? Anyway, stopping here. So gradient descent can be sped up by incremental updates, and convergence can be improved using smoothing techniques like RMS prop and Adam. We'll continue in the next class. Yes, Talha?